Hey y'all. So I wanted to talk a little bit more about what we were looking at in class. So just a quick kind of reiteration of that is we started by looking at the energy of two carts as they ran into each other. We looked at two different situations. One where the carts had magnets and kind of bounced off of each other that way, and then one where they had Velcro and when they collided, they moved on together. They kind of stuck together and moved together in that way. Now, what we did is we created a chart, kind of like this one over here, and we calculated the initial kinetic energy of one cart and the initial kinetic energy of the other cart by doing 1/2 mv squared, and we were able to calculate the total kinetic energy of our system, of the two carts added together. And then we did the same thing after the collision. We found their final kinetic energies, and we added those together to get the final after. And what we noticed in both situations was that we lost some energy. Now, depending on the situation, with the magnets, we found that we lost somewhere between 10 and 20% of our energy during that collision. With the Velcro, we found that we lost about a third of the energy, about 31% right here for one class. So it varies depending on the actual collision that takes place, but the idea is we lose energy. We also talked about the idea that we don't really like to say that we lost energy because energy isn't really ever lost. It's converted into other forms and things like that, but it's not ever really lost. And so what we want to do is we want to make sure that we understand where it went. We talked about the fact that energy could go to sound, energy could go to deformation when things kind of bang into each other. It could go into vibrations, which then connected with that it could actually go into sound. Sound waves are a transfer of energy from wherever that sound is coming from. So lots of different places that energy, that kinetic energy that we had in the beginning could go so that we end up with less kinetic energy than we started with. We then looked at this new idea of momentum, and we actually ended up, in my second class, we ended up with this one over here, which you'll notice we ended up with almost exactly the same amount of momentum in the beginning and end. And the reason for that is that momentum is conserved. In any type of collision, momentum is not lost. Momentum is conserved. We have the same amount, total amount of momentum initially, and the same total amount of momentum finally. We'll look at that a little bit more in class next time, but what I wanted to talk to you about right now are three different types of collisions, actually four different types of collisions that we may see in our class. All right? Now, the first one is something called an elastic collision. Now, elastic collisions don't actually really ever happen. An elastic collision is when two things bounce off of each other and there is no energy lost. And so we could say that the initial kinetic energy is equal to the final kinetic energy. We would get no change in energy. The total energy before and after would be exactly the same. Now that doesn't really happen because of deformation and because of sound and other things, right? We can get close. When we use magnets, it's not that bad. When we look at like pool balls, they're really, really hard and actually does transfer most of the energy from one ball to the next. We tend to get pretty close, but there's some sound there. If there's some sound, it means there must be some energy loss. So, as we look at these situations, we'll recognize that perfectly elastic doesn't really ever happen. But we will make some assumptions sometimes and say this is almost elastic. So we're going to treat it as elastic. So that's the first thing to remember, is that in a elastic collision, the kinetic energy is conserved. The total amount of kinetic energy before equals the total amount of kinetic energy after. The second type of collision we'll see is an inelastic collision. Okay, inelastic, I-N-E-L-A-S-T-I-C, inelastic. Now, in an inelastic collision, energy is not conserved. All right, now most collisions that we see are inelastic. All right, even the one with the magnets, which we said that's pretty close to elastic, in that one we lost some energy. And so that was an inelastic collision. That means the total energy at the beginning is not equal to the total energy at the end. In fact, we lose some energy there in an inelastic collision. It's being turned into other forms. We do want to make sure that we recognize what forms, where that energy is going. Okay? Your third type of collision is something called a completely inelastic collision. Now, in a completely inelastic collision, that's like what we saw with the Velcro. When two objects run into each other, they stick together and they move together afterwards. So that would be a completely inelastic collision. All right? Completely inelastic. And so in that situation, energy is not conserved either. We actually saw that we lost about a third of the energy in the one that we did in class. Okay? So those are the first three. Those are the ones you're going to see most often. Now, there is one other type of collision, or one other type of, I keep saying the word collision, but really we're looking at interactions here. One more type of interaction or collision is something called a super elastic collision. Okay? Now, in a super elastic collision, we actually end up with more energy than we started from, right? You could think of like a grenade, right? A grenade, there's no energy at the beginning, everything's at rest, but then when it blows up, you got all sorts of kinetic energy going everywhere. So in that situation, we end up with more kinetic energy than we started with. That energy's got to come from somewhere. In the case of the grenade, there's some chemical potential energy that turns into that explosive kinetic energy. Somebody in one of the classes asked about a rocket the other day. So a rocket has chemical potential energy in it, which when you combust it, it turns into kinetic energy that then can be transferred to your rocket. So super elastic means that we end with more energy than we started with. Okay, now most collisions will not be super elastic. There's got to be something there where we're turning one of those potential energies into kinetic energy in order for super elastic to actually work. Okay, so those are your four types of collisions. Make sure that you recognize those. Elastic, meaning that kinetic energy is the same before and after. Inelastic, which means that energy is lost. A special form of that, completely inelastic, which is where they stick together and energy is lost. And then super elastic, which is where energy is actually gained through the interaction. Now, in all of these, momentum is conserved. This is why momentum is so cool. All right, this idea of momentum being the mass times the velocity, this is conserved. The total momentum before the interaction and the total momentum after the interaction should be the same as long as there are no outside forces. Now, if there are outside forces, then you can lose some momentum due to those outside forces. And we'll talk about that a little bit in the following class, okay? But for now, I want you to recognize that as long as there's no outside forces, and a lot of times in an interaction, if the interaction happens quick enough, we can say during this interaction, we can basically ignore outside forces, even friction sometimes. During that collision, friction is going to be so minimal, or if that collision happens really fast, friction may not cause it to lose any momentum at all, or at least not an amount that we notice, all right? So we've summed up what we learned in class. We've talked about the different kinds of collisions. What I want to do now is show you an example of how we would actually use this in order to solve a problem. We're going to look at an example of a football player, okay? American football player. In American football or rugby or any of those, tackling sports, you got somebody that goes and slams into somebody else and tries to knock him down to the ground, all right? Now, as you know, in those sports, it is very helpful if you are large, whether it be large muscular or large because you just got big bone body, whatever it is, being large, being tall, having a lot of mass is important, all right? Now, I want to give you an example and show you why it's so important, all right? So let's consider this. I have a mass of about 90 kilograms, okay? So here's me at 90 kilograms. And I'm just standing there. We could say that I'm running along, but let's just, for the sake of argument, say that I'm standing there. My speed is 0 meters per second. Okay? Now, if someone smaller than me tries to tackle me, okay, so let's say my daughter. My daughter is probably way less than half my mass. So here's my daughter. My daughter is running as fast as she can 30 kilograms. She's going to run at me at a speed of 7 meters per second. And she's running as fast as she can in this direction, right at me. Okay? So let's look at momentum here, because obviously there's an imminent collision here, right? She's going to try to tackle me. She's going to try to take me down. Let's see what happens. Now, in football, they always teach you to wrap up, okay? They teach you that when you collide with them, you should wrap up, you should hold on to them. So we're going to treat this as an inelastic collision, where the two objects stick together during the collision. All right? So what we're going to do is we are going to try to find out what happens during the collision. So we're going to make a table. We were doing this before. All right. We've got the initial. We've got the final. We've got me. We've got my daughter. We'll say, I don't know which daughter this is. We'll just say daughter. No, we're not, because I don't want to have to spell that. We're just going to call her Lily, because she's the easiest one to spell. All right, and then we've got the total. Now, we're going to look at momentum here. We're not looking at energy, because we know that in the collision, energy is going to be lost, and it's or turned into other forms, and that's difficult to be able to figure out exactly how much has been turned into other forms. So we're looking at momentum here. Remember, momentum is equal to the mass times the velocity. That's it. So initially, my mass is 90. My velocity is 0. So 90 times 0, we already know is going to be 0. Lily's is going to be her mass, which is 30, times her velocity, which is 7. She's moving to the left, so I'm going to call that a negative 7. All right? And is not equal to 0. That would be negative 210. And remember, the units are kilogram meter per second. And so the total momentum initially, before she runs into me, is a total of negative 210, right? Kilogram meters per second. Now, what happens after the collision? Well, after the collision, I now have a mass of 90 still, but I now have some velocity, right? Because she's run into me, and something's going to happen. We're going to ignore friction between our feet just for a moment, and I've got some velocity. What that velocity is, I don't know. But watch this. Because she's going to have 30 kilograms, and she's going to have the same velocity, right? Because she's doing what she's supposed to. She's tied up. We're moving along at the same speed after she runs into me, all right? Now, if she doesn't, she's probably just going to bounce off, right? So she's going to do what she's supposed to. She's going to hold on tight. We're going to move along together. So same velocity. We're going to move in the same direction here. Now, the total is going to be those two added together, right? So we go 90V plus 30V. Now, what we can do, because we know that the initial momentum should equal the final momentum, is I can now write an equation. I've got an equation that says that negative 210 is equal to 90V plus 30V. I can go ahead and add those two together. 90 plus 30 is 120. And then I should be able to divide. And if I take 210 and I divide by 120, then I get 1.75. I do get negative. And you'll notice that that's not very fast. Okay? Can she get me moving? Yeah, but not very fast, because the momentum must be conserved. All right? Now, what if we have a bigger person now, right? We were talking about the idea of American football, that the big guys tend to fare a little bit better, right? Well, what if, same speed, but what if we have somebody that's a little bit bigger than me, right? Somebody that's got a little bit more muscle on their bones. I know it's hard to believe, but somebody that's got a little bit more swole than I am, right? So let's say that we got somebody that's 110 kilograms, okay? A little bit taller, a little bit bigger than me, all right? So 110 kilograms. So how would that now change what we have here? Well, we could go through, we do exactly the same thing, but we're going to change some of our masses around, right? So my initial momentum is the same. That doesn't change. Then here, instead of being 30 times -7, this is going to be big boy. Okay, so I'm going to go 110, because that's the new mass, times 7. So that's going to give me -770. All right. And so I get a total of -770 kilogram meters per second. All right. Now, when big boy runs into me, my momentum is going to be 90 V. His momentum is going to be 110 V. Right? Because he's going to go the same speed as me. He's going to wrap up. We're going to move along together. Okay? And we can add those together. So 90 V plus 110 V. And when we put those together, we should end up getting -770 is equal to 90 V plus 110 V. And we divide, and we should get whatever 770 divided by 200 is, 3.85. Now, you'll notice that that is a significantly larger change for me, right? I was stationary, and now I'm moving almost 4 meters per second. Right? That is a huge difference compared to when my daughter Lily, at the same speed, ran into me. This is the value of conservation momentum. It allows us to figure out those things where energy is clearly lost. If you've ever watched an American football game or a rugby game, you can hear it when those people are slamming into each other. Okay? Now, of course, those situations are a little bit more complex because they're still pushing off the ground. There's probably some additional force there. The guy that's getting tackled has got some cleats. He's trying to push back the other direction. But in the basic, simple scenario of just looking at the momentum of those two bodies clashing into each other, you can see how I'm going from 0 speed to this speed, which is a pretty big change in a pretty short time. That's me getting tackled. All right? It definitely makes a much bigger difference with a big guy versus a small guy. And that's why American football players and rugby players tend to be big, bulky guys. Just like me. Right? All right. So that's it for today's video. I hope you got used to, I hope that was helpful in kind of reviewing what we talked about in class. Talking about the different types of collisions, which we're going to see a lot more in class next time. And lastly, just kind of giving you an example of what we would use momentum for and how it connects to sports. All right, so I'll see you in class.